knows the storm is coming fast, the day will soon be here, when those who are caught unprepared will be the first to fall, that much is clear.
Hello and welcome to Physical Attraction, the TEOTWAWKI specials, where we'll be examining the end of the world, one apocalypse at a time.
And survive while there's people crying, people dying everywhere around.
Hey all, and welcome to this TEOTWAWKI special of Physical Attraction. This episode is called It Came from Outer Space. On the 30th of June 1908, the people of Russia got lucky, for once. In an incredibly remote region of Siberia, near the Tunguska River, there was an explosion with the power of 1,000 atomic bombs. People on the ground reported hearing a tremendous pounding as if they were being bombarded by heavy artillery fire. The explosion was powerful enough not only to be seen for hundreds of miles, but to knock people off their feet for hundreds of miles. 80 million trees were blasted aside, and the explosion magnitude was big enough to be measured on the Richter scale as a 5.0. A local newspaper described the event. As the body neared the forest, the bright body seemed to smudge and then turned into a giant billow of black smoke, and a loud knocking, not thunder, was heard as if large stones were falling or artillery was fired. All buildings shook. At the same time, the cloud began emitting flames of uncertain shapes. All villagers were stricken with panic and took to the streets. Women cried, thinking it was the end of the world. This was the Tunguska fireball event, and it got its name for good reason. The spreading fireball and blast wave from the initial shock was huge. When scientific investigators reached ground zero for the event, they saw an amazing sight. For 8 miles around, the trees were still standing up, but they'd been burnt to a crisp from the tips of the branches down to the roots. Further out, further than the eye could possibly see, the trees had been flattened. The Tunguska event was caused by a meteorite, comet or asteroid that intersected with Earth's atmosphere and rapidly heated up as a result. Under the immense pressure, the meteoroid exploded in mid-air, unleashing the massive fireball. This explains why the trees near the centre were still standing. The blast wave, expanding in a sphere from several miles up in the sky, was travelling almost directly down from the atmosphere and not horizontally in this zone. Had the Tunguska meteoroid impacted a centre around where anyone lived, there would surely have been thousands of fatalities. If it hit a city, such as Moscow or New York, millions would have died in the searing heat of the explosion. It is fortunate that the impact hit a sparsely populated region and there were very few casualties. The Tunguska event was unusual. Such impacts occur maybe only once every 300 years. Yet the Earth is constantly being bombarded by debris and detritus from outer space. 20 to 40 tons of it hits us every day. Even a rock the size of a fist can be moving quickly enough and burning brightly enough to be seen as a shooting star in the sky. The object that caused the Tunguska event was likely a few dozen yards across. Had it actually struck the ground rather than exploding in mid-air, the crater left behind would likely be a few miles across. It's now pretty much accepted universally that 65 million years ago, an asteroid impact caused the last great mass extinction, at least before the present one which is being caused by humans, and wiped out the dinosaurs. A rock the size of Mount Everest, around 6 miles in diameter, smashed into the Earth off the Gulf of Mexico. The explosion was 1,000,000 times more powerful than if every single nuclear weapon on Earth was simultaneously detonated. A big chunk of the Gulf would have immediately evaporated into steam as the asteroid approached. Its impact threw vast amounts of molten rock and steam into the air in a vast plume, which rained fire down upon the rest of the world, with many smaller chunks of the Earth being thrown up, then caught in its gravitational pull and smashing back down, in places hundreds of miles from the initial event, causing a devastating chain of forest fires which filled the sky with smoke. The tsunami which spread from the event would have been hundreds of metres high. For scale, a normal tsunami like the Boxing Day tsunami in 2004 might have had waves up to 30 metres high. What's more, a normal tsunami might move at the speed of a car. This tsunami would have moved faster than the speed of sound, smashing into the coastline around Mexico and North America. Whatever creatures did survive the initial apocalypse of this event would not have it easy. As you might imagine from our episode on supervolcanoes, this impact threw a vast amount of dust into the atmosphere, which kicked off another ice age. Any surviving dinosaurs couldn't adapt to the changing temperatures and quickly died out. So it was a good time for the small mammalian creatures that would one day evolve into humans. If such an impact occurred today, there's no question that the human race would struggle to survive. Billions, not millions, would be killed. If you want to stay awake at night, you should know that there are plenty of chunks of space debris of similar size to the asteroid that wiped out the dinosaurs. Not only that, but there are several orbiting around the Sun whose orbits actually cross Earth's orbital path. Every orbital period we manage to miss each other, but at some point in the future we're not going to be so lucky. And asteroids are far from the only astronomical phenomenon that has the power to kill us all. As you can imagine if you listen to our early physical attraction episode on stellar formation, there are processes out there with ridiculous amounts of energy that would vaporise the Earth without breaking a sweat. A gamma-ray burst, for example, that had the Earth in its path would fry the planet easily. Massive solar flares are also a concern and could disrupt our technology. A nearby supernova could shower us in deadly cosmic rays if it doesn't toast us directly. And of course, as everyone knows, the Sun will eventually expand and engulf the Earth. To my mind, the really scary aspects of this kind of apocalypse is that there's no good news. It's completely outside of human control, and the forces involved can be so dramatic that there's really nothing we could possibly do to shield ourselves, short of colonising other planets. In the case of a supervirus or a supervolcano, you can shield from it in some ways. But in some of these cases, the forces involved are just far too much. The other scary aspect is that, due to the finite travel time of light, a nearby supernova could have already occurred. Even now, the deadly explosion could be hurtling towards us at the speed of light, and it would take years for us to realise. If the Sun vanished tomorrow, it would take 8 minutes for anyone on Earth to know about it. And there was a very large supernova in 1054, which was observed in 1054, but the material from that supernova that's going to land on Earth hasn't reached us and won't reach us for another few thousand years, but it's still hurtling through space towards us. Luckily, by the time it gets here, there'll only be a few tons that will land on Earth and it won't make a huge difference. So there's a grim sense of fate about this kind of destruction. Maybe the asteroid is already on course. Maybe the gamma rays are already flooding towards us, and it's already too late for any human actions to prevent our doom. But how likely are any of these Earth-scale astronomical apocalypses to actually happen? And can we do anything about it? Working this out is basically like dividing two massive numbers. One is the vast array of things and events in the universe that could kill us without batting an eyelid. And the other is the vastness of space, that mean that the chances of being in the same coordinates as such a deadly event might be quite low. And on the whole, the vastness of space does win. Let's look at the asteroid impacts first. I mean, there are people out there who are tracking this stuff, right? Right? Well, yes, thankfully there are. And these people have some of the coolest jobs in the world out there, in my opinion. Keeping the world safe, albeit from an event that has a low probability of occurring. In 1992, NASA first started the search for near-Earth objects. Now these are those asteroids of greater than 1 kilometre across that would cause truly global destruction if they hit. Since then, the target for the year when they would have tracked these objects has been continually revised upwards, as it's proved more difficult than people thought. Scientists have pushed back the date by which they wanted to have discovered 90% of NEOs several times. They now hope to have them all tracked by 2020, although it's worth pointing out that there are still plenty of smaller objects, the size of the one that caused the Tunguska event, such that it's just too difficult for us to see and track all of them, and we likely won't get a warning of an impact from some of those until it happens. An example would be the small meteoroid that exploded in the air over Russia in 2011. Given that we might expect a Tunguska event-type impact every few hundred years, there's a decent chance that another one might occur in your lifetime. Hopefully it will once again miss the populated regions of the Earth. Even amongst the larger NEOs, new discoveries are being made all the time. In 2009, another large NEO was discovered that was previously unknown to astronomers. So far, none of these are projected to hit the Earth anytime soon, although there are occasional near misses that scientists worry slight deflections could cause an impact. In 2004, for example, our best observations of 99942 Apophis, a 370-metre asteroid, suggested that it had a 3% impact chance of the Earth in 2029. And people were also concerned that if it missed the Earth, it would go through a gravitational keyhole around the Earth, where the Earth's own gravity would pull it back and cause it to smash into the Earth within the next century. Now, better observations have since decreased this possibility to almost zero. We're now very confident that whatever happens, it will be another near-miss event. When we say a near-miss in these terms, it will miss us by around 6 times the radius of the Earth. It's a close approach, but not hugely threatening, although it might make you worry when you realise that that's closer to Earth than many weather satellites. Observing these objects is difficult. We can never be completely certain of our measurements, so like all good scientists, things are expressed in terms of a probability, and you can look up the various probability tables that each near miss could in fact turn out to be a collision. Our measurements are wrong in such a way that the near miss could in fact be a collision. But if you look up these tables, you'll see that they don't add up to all that much at the moment. So there is a small chance that either our measurements for an NEO are catastrophically wrong, and it will in fact hit us, or that there's some large NEO that we've somehow missed that might impact us. But it seems unlikely, because we're pretty good at tracking them now and calculating their orbits to high degrees of precision. There's always some uncertainty. So for example, in this apophysis case, people weren't sure about how the gravitational keyhole might work. It now seems unlikely that it will work that way, but it shows you why uncertainties in the orbit are concerning, because a slight uncertainty in the orbit can be multiplied by the gravitational influences of other objects. Now the smaller objects are trickier to see, but they don't pose an apocalyptic threat, unless you happen to be underneath one. You might not believe this, but people actually have been hit and have had their cars destroyed by small meteorites in the past few decades. It's exceedingly rare, but it does happen. Imagine trying to get your insurance to pay out on that. One woman, it's a bizarre story, she was hit by a meteorite that fell into her room and ricocheted off a cabinet and gave her a bruise on the leg. And although she wasn't lastingly hurt, actually it turns out that the fame and publicity that she got from being hit by the meteorite contributed to a nervous breakdown that may have led to her premature death. So in some ways, the meteorite casualties for humans are far from zero. So what would happen? Let's say that we observe a new or existing near-Earth object and calculate that it has a very high probability of smashing into the Earth. Well, if you've seen the film Armageddon, you'll know that Bruce Willis's strategy is to nuke the asteroid to blow it up. But that's actually unlikely to be incredibly successful. For a start, most asteroids are less dense than solid rock. That means that it's far less likely to be fragmented by an explosion. You can imagine the difference between hitting a block of water with a hammer and hitting a block of ice with a hammer. The ice might fragment, but the water is less dense, and it won't. An explosion might heat up the asteroid somewhat, but it wouldn't destroy it completely. And think about it. Even if you do detonate a warhead with enough power to fragment an asteroid, and it succeeds in blowing it up, then what actually happens? Well, a lot of near-Earth objects are thought to be more like piles of rubble, loosely bound by gravity. So an explosion might be able to blow them apart, but then you just have a shower of smaller meteorites that would be smaller, more difficult to track, and cause more widespread destruction, on similar orbits, and they'd still impact the Earth. And unless you could guarantee that all of the big lumps in the near-Earth object would be broken down, so that everything would burn up in the atmosphere, it's a risky strategy. So asteroid impact avoidance strategies, and yes, there are people out there whose job it is to come up with ways of avoiding us being hit by asteroids, which is marvellous. But they tend to focus on deflecting the asteroids instead. You want to keep it together. The logic is simple. If you can hit the asteroid at a far enough distance away, even a deflection of a tiny angle would take the asteroid's orbit out of the path of the Earth. If you hit the thing far and away enough, you only need to change its speed by a few millimetres a second, and you can make it miss Earth entirely. Equally, if you can slow down the asteroid as it approaches, it gives the Earth time to move out of the way, if you see what I mean. The orbits no longer intersect, such that the asteroid is in the same position as the Earth at the same time. These methods are generally considered more feasible than destroying the asteroids outright. Scientists confirm the potential for these methods using the brilliantly named Z machine. This machine is like something out of science fiction. It's the closest we've ever come to making a giant death ray. It produces the highest frequency electromagnetic radiation that humans can make. You can go back and listen to our episode on radiation if you want some more details. It can produce plasmas with temperatures up to 2 billion Kelvin, and so they mostly use it for weapons and nuclear fusion research. But it was once used to fire X-rays of the same kind that would be generated by a nuclear bomb at some asteroid-type material. You see, the issue with detonating a nuclear warhead in space is that because things are not very dense in space, the explosion is not going to push things out in a shock wave or a blast wave. Instead, the vast majority of the pushing is done by the X-rays that are produced as the nuclear chain reaction goes on. So they use the Z machine to fire X-rays at an asteroid-type material, and they confirmed that it would be capable of deflecting a near-Earth object. The key is to detonate the bombs a few hundred metres away from the object, so as to push it aside without fragmenting it. Now you can think of ways of doing this without nuclear weapons. A non-nuclear alternative would involve ramming the asteroid with a high-speed projectile to knock it out of the way. and again, if you can hit it at a far enough distance, you can divert the orbit enough to miss the Earth. And scientists have had some success with these so-called kinetic deflectors. We smashed a 1-ton brick into a comet in 2005 to study its composition, and that went off fine. And it's even been suggested that we could manipulate the asteroids in more subtle ways. If you can get a rocket up to the asteroid and still have control over the rocket, the gravitational pull of the rocket's mass on the asteroid can actually disrupt its orbit enough to cause it to miss the Earth. So the rocket pulls on the asteroid with its gravity, and that is enough to make it miss the Earth completely. Phil Plait, in his wonderful book Death from the Skies, which deals with these threats, notes that you could even try and use this type of technology to drag an asteroid into orbit around the Earth. And then we could use it to our advantage. There's lots of minerals in asteroids and metals that aren't found on Earth that often. Trillions of dollars of valuable minerals might be buried in an asteroid of the right composition. Instead of being an existential threat, it could be a lucrative asset. Although, to be honest, I can't imagine people would be very happy if a billionaire like Elon Musk says, "Guys, I'm just going to launch a rocket and, capture this asteroid which I will then mine for trillions of dollars of profit." People might be a bit concerned that if he gets his maths wrong, it'll smash into Las Vegas. But what's the present state of play from the threat from asteroids? Now, none of the methods for deflecting them are mature technologies yet, but they're not so far from being realised that they could never happen. It seems pretty likely that the only lack here is a lack of investment. Providing we had a decent amount of notice, maybe 10 to 20 years for a potential impact, which is actually the kind of timescale we do get because we can calculate the orbits so well, a concentrated effort on the part of humanity should be enough to avert this kind of disaster. It wouldn't be cheap, and it wouldn't be pretty. But actually, don't you think this is amazing? We can genuinely imagine that we'd probably be able to knock a comet aside and save the planet. This has never been true for any species before us. Eventually, there will be an impact, but odds are that we're pretty good that we'd be able to avert it. There is a concern though, and the concern is comets, not asteroids. Comets are icier and gassier than asteroids, which are essentially lumps of rock. They're often in much wider, larger, more elliptical and unpredictable orbits than asteroids, and they don't go around in the same galactic plane as we do. As they spin and emit jets of gas that can knock the comet into different orbits due to bits of the comet melting or not melting, they're far, far harder to predict. So the Hale-Bopp comet, that was only detected a couple of years in advance of it being sighted. Incidentally, the Hale-Bopp comet was also the comet that led to the mass suicide of the Heaven's Gate cult. They believed that they'd board a spaceship to paradise on the comet. No word if that actually happened. That comet had a solid nucleus 25 miles across, much bigger than the asteroid that wiped out the dinosaurs. A comet impact of that size would almost certainly destroy the human race, and we might end up with far less warning about a nearby comet, or the fact that its orbit could change and intersect ours fairly late on. So, just in case, you should write to your local elected representative and ask them to fund research into deflecting these things. The probability of you being killed by an asteroid or meteorite strike in your lifetime has been calculated at around 1 in 700,000. But with the proper technology, we could reduce this to practically zero, and actually, for once, remove a threat to the planet. But what about the other things I've mentioned? Solar flares, gamma ray bursts, supernovae. Let's describe these events, the potential impacts they'd have, and then the overall threat assessment. The Sun is a big ball of plasma. Its own gravitational pull balances the outer force of the nuclear fusion happening in its core to hold the Sun together. Yet, because it's made of charged particles that move in complicated, convective ways, see our early episodes on stellar formation for an example of this, it has a magnetic field that's incredibly complicated. The field of physics that studies magnetic fields in plasmas is called magnetohydrodynamics, which is wonderful to say and read. But it can give rise to complicated behaviour. Great tongues and conveyor belts of gas and plasma, hundreds of miles long, lick their way through the Sun, generating complex, tangled webs of magnetic fields. As magnetic field lines get tangled up, they interact with the plasma on the Sun's surface as well. And this can change the way that the gas can move in the Sun, and prevent the hottest gases from reaching the surface in some regions. So the Sun's surface is not uniformly bright, it's not the same brightness all the way around. You get sunspots where the coolest gases are concentrated on the surface. That sunspot activity follows an 11-year cycle, that corresponds to the magnetic field activity in the Sun. Sometimes there are plenty of sunspots, and sometimes none at all. But inevitably, the magnetic field can't keep the rising hot gas down forever. And so it behaves like a big spring. The field lines store more and more energy as time goes on, with the gas pushing against them. Eventually, and sometimes catastrophically, the magnetic field reconfigures itself, and there's a huge release of energy close to the Sun's surface. This is what we call a solar flare. One was observed in 1859, and even then, with Victorian-era technology, we could measure the fluctuations of Earth's magnetic fields because of the flare. Subsequent flares have sent bursts of protons travelling at half the speed of light towards the Earth, and flares can be accompanied by blasts of X-rays. It's this kind of flare activity that's part of the reason our planet badly needs its atmosphere. Without something to absorb the X-ray bursts, we'd all suffer from radiation damage. Solar flares will occasionally toast communication satellites. Much more massive types of flares, such as coronal mass injections, could wreak havoc with the Earth's magnetic field, with only a few days of warning provided. Some of these CMEs have already occurred, but luckily they weren't pointing straight at us, so they only produced aurorae. The northern lights, for example, are caused by accelerating charged particles caught in the Earth's magnetic fields, and lots of these come from the Sun in CMEs. The real risk to humanity is down to the fact that we have an awful lot of things that are very sensitive to magnetic fields down on Earth. Our entire society rests on a simple electromagnetic fact. When you move a wire in a magnetic field, a current is generated. It's this principle that's in play of all of electricity generators of any kind on Earth. All they are is just different ways of moving wires in magnetic fields. And the world is covered in a vast network of wires, the electrical grid. If Earth's magnetic field is severely disrupted, it can cause vast surges of current that could severely damage the grid. It would be a rare solar flare that would cause the kind of surges that would blow up power stations and set power lines on fire, but there's no question that it could happen. And there's not an awful lot we could do about it if it did. It's possible to surge protect the grid, but the thing about the grid is that a lot of it is more often than not old, overloaded, difficult to repair and replace. I mean, this is to the woe of people who want to make it more flexible to deal with renewable energy. Think about it like this, though. How many policymakers would even think of solar flares as a threat to the grid? The other astronomical threats to our planet come from outside our solar system. We talked about supernovae in the stellar formation episodes, but not about their destructive potential. If our sun went supernova, it won't. We'd be toast for sure. And there are probably many millions of scorched planets flying around in distant regions of space, which were violently ejected when their parent star went supernova. But what would happen if a supernova went off in our galaxy? How close would it have to be for us to seriously worry about it? The nearest star to Earth that has a potential to go supernova is Spica, 260 light years away. In terms of actual debris from the supernova, we'd probably be fine. Although it ejects a massive amount of material, this is dwarfed by the massiveness of the distance from us to the supernova. There was a supernova in our galaxy in 1054 that formed the Crab Nebula. It was bright enough to be visible alongside the Sun during the day for several days. And even though it was close by, only a few tons of material ever made it to Earth. Even a supernova that was only a few light years away is unlikely to directly destroy the Earth via the matter that it sprays everywhere. The bigger risk is from radiation. Now, there's no star close enough that might go supernova, which could produce gamma rays and X-rays strong enough to sterilise the Earth for life. The atmosphere would probably absorb a lot of them. The only issue is that in doing so, the atmosphere would be badly damaged. Specifically, if a supernova happened between 25 and 100 light years away, it would probably produce enough gamma rays to strip the Earth of its protective ozone layer. Then we would no longer be shielded from UV radiation from the Sun, and it's this that would cause the real damage, causing increased rates of skin cancer due to the radiation, sure, but also playing havoc with the delicate ecosystem of bacteria and phytoplankton that form the base of the food chain. Would a supernova actually wipe out life on Earth if it occurred within a few dozen light years? One of the things that's interesting about this particular theory is, well, most of our apocalypses we don't get to test because they've never happened before. But it seems that there might have been a supernova nearby a few million years ago. Geologists have found a rare isotope of iron that's only produced in supernovae, and that was deep inside the Earth's crust. Based on where it was located and the amount that they found, we can infer that a supernova might have deposited this on the Earth's surface a few million years ago, and it was probably only a few hundred light years away at most. And this is reassuring because it implies that if gamma ray impacts from a supernova a few million years ago weren't enough to wipe out life then, they probably won't be now. One thing is for sure, if a supernova did occur at these kinds of distances in our lifetimes, it would be a spectacular sight. You won't need a sensitive scientific instrument or telescope or neutrino detector to realise that this cosmic event has occurred. It could shine alongside the sun during the day. It would brighten the night. And since one occurs in our galaxy every century or so, your chances of seeing a supernova during your lifetime aren't that bad, but you'll likely only get one shot, so make the most of it. Gamma ray bursts are rather mysterious events for astronomers. It's not entirely settled what causes them. They're very rare but very powerful, far more powerful than supernovae. They are in fact the most powerful astrophysical events that we know about. The main theory is that they occur due to black hole formation, which beams matter in an explosion of heat and magnetism into highly collimated blasts. They're powerful enough that one, which occurred 8 billion light years away, was even visible to the naked eye. Phil Plait calculates that if a GRB occurred 100 light years away, it would create a beam 50 trillion miles across that would easily engulf the entire solar system. In the space of a few short seconds, it would dump so much energy onto the Earth's surface that it's equivalent to blowing up a nuclear bomb over every square mile of the Earth. It would almost certainly instantly sterilise the Earth, killing all life on the surface, and maybe a few metres down into the oceans as well. It would be left to deep-sea life and maybe anyone hiding underneath thick, thick layers of lead or deep in mine shafts to repopulate the planet, which would be made difficult by how radioactive the surface would become. Definitely the end of the world as we know it. Luckily for us, there are a couple of factors that save us from this horrible scorching from GRBs. One is that they're very beamed phenomena, like we said. All of the radiation is focused in two strong beams, which means that if the direction is wrong, the gamma ray burst will miss you altogether. Think of them as cosmic death rays rather than explosions. So for example, the nearest GRB candidate is oriented at 45 degrees to us. When it does explode, which could be in millions of years, it will be an amazing astrophysical phenomenon, but the most devastating effects will likely miss the Earth. The other is the distance. Even the closest thing that could become a GRB is 7,500 light years away. Now at this distance, the gamma rays will still cause immense damage, including, due to their effects on the atmosphere, acid to rain from the sky, and the electromagnetic pulse from the blast would wipe out any electronic device. Bizarrely, because the gamma ray burst is so short in duration, and because the EMP would be absorbed by the Earth, this effect is likely only to occur on one half of the Earth that was facing the GRB when it occurred. Can you imagine that? Half the Earth having no technology, and the other half being basically unscathed? Yet gamma ray bursts are likely one of the cases where the vastness of space does dwarf the vastness of the explosion, even in the case of the biggest energetic events in the universe. It seems very, very unlikely that one is about to fry the planet, even though if it did, there would be absolutely nothing we could do about it. Whole sections of the universe are being wiped out for life by these cataclysmic events, but luckily for us, there's a lot of universe to go around. I have to say, this has probably been the most reassuring episode for me to research. Going in, I knew a lot about the titanic energies and various scary phenomena in the universe that could easily kill us at all if we were close enough. And it's a very scary scenario because for a GRB or a supernova, you would expect little warning and no possibility of saving yourself from the destruction. But it seems that the distances to most of these objects are just too far for there to be any major risk from them. Asteroids and meteorites are a much bigger threat, and have been historically, just ask the dinosaurs. But we're actually reaching the stage where human technology is getting good enough for us to defend ourselves from flying chunks of space debris. A more robust tracking system combined with the technology to deflect the rocks, and we should be safe. So it's lucky that the most dangerous and likely threat is also the most preventable one. Of course, astrophysics will eventually kill us all in the end. Even if we escape our planet before the sun expands and engulfs the Earth in a few billion years, we'll still die eventually due to the inevitable heat death of the universe. But given that human life expectancy is pathetically tiny compared to the life expectancy of the universe, I'm not going to lose any sleep over it. Thanks for listening to this TEOTWAWKI special. I hope that I've been able to reassure you about the fact that outer space is not going to kill us anytime soon. If you've got opinions about whether it will kill us anytime soon, Well, you can tweet me at physicspod, email us at physicspod@outlook.com. You can find us on Facebook. Any questions, concerns, things you think I've got wrong, things you think I've got right. It's good to hear all of it. And leave us a rating and review on iTunes, your favourite podcast provider. Tell your friends who are concerned that the world is ending, or that chap you know who has a Nibiru t-shirt. And next week we'll be talking about a different apocalypse. Until then, stay safe.
You better make some preparations. There's no time for hesitations. Compile a list of tips.
Our theme music is Get Ready for the Apocalypse by Astrometrics.
To get ready.